In this example for spanning sets and subspaces, we want to show two subspaces are actually equal. So the question we want to look at is, suppose U1 to UP and V1 to VQ are in a vector space. We're going to let H equal the span of the UIs and K equal the span of the VIs. And we're going to define a set H plus K to equal the set of W and V, such that W can be written as a sum of a vector in H and a vector in V. So what we want to show is that this H plus K that we've now defined is actually equal to the span of U1 to UP and V1 to VQ. So in general, to show two sets are equal, we have to show that each is contained in each other. So what I mean by that is, if we want to show A is equal to B, where A and B are sets, we need to show that two things happen. A is a subset of B, and B is a subset of A. So for our particular purposes, we want to show that H plus K is a subset of S, where S is the span of those vectors. And the second thing is S is a subset of H plus K. So let's go ahead and do that. So let's first show that H plus K is a subset of S. So what we need to do is we need to take an arbitrary vector in H plus K and show that it can be written as a span of U1 to UP and V1 to VK. So by definition, W is equal to some vector U plus V, where U is in H and V is in K. Then again, by definition, there exists Ci, real numbers, and Di, real numbers, such that U is equal to the sum of Ci Ui, where I goes from 1 to P, and V is equal to the sum of Di Vi, where I goes from 1 to Q, since U is in H, which is the span of the UIs, and V is in K, which is the span of the VIs. Then just rewriting W, we get that W is equal to C1 U1 plus CP UP plus D1 V1 plus DQ VQ. And this is precisely what it means to be in the span of the UIs and VIs, so that W is actually in S. So we've shown what we needed to show. Any vector W in H plus K is actually an element of S. Next, we need to show the other direction. We need to show that S is a subset of H plus K. So we do this in a similar manner. We let X be any element in S, and we have to show it's an element of H plus K. Well, by definition of being in S, that means that X is a linear combination of the UIs and VIs. So X is equal to A1U1 plus APUP plus B1V1 plus BQVQ for some constants AI, BI, and R. Well, this first part then, notice, is just a linear combination of the UIs, which means that it's an element of H, since H is the span of the UIs. And the second half is an element of K, since it is a linear combination of the VIs, and K is equal to the span of the VIs. So that means that we can write X to equal the sum of some vector U and V, where U is an element of H and V is an element of K. So that means then we have shown that x is actually an element of h plus k as well. And so we're done because we wanted to show that h plus k is equal to the set S, and to show that we have to show h plus k is contained in S, and S is contained in h plus k. So we've concluded the proof.